Yeah. Mm-hmm. Okay. Oh. 你是黄淑婷哦，好，Yeah. Okay, so today is the last lecture, and it will be just 1 hour. Okay, so we'll end at 4:20. So today I want to talk about the equivariant Carton theorem and outline its proof and discuss some of the consequences. Okay? So last time we showed that the Weyl model is isomorphic to the Carton model. So let me recall the Carton model for a compact connected Lie group. Oh, no, just a minute. Let's see. I think we only assume that the group is connected. We don't need to assume that it's compact. Okay? So for connected Lie group. And the reason we need connectedness is that we wanted to use the condition for invariance, that an element is invariant if and only if the Lie derivative with respect to any x in the Lie algebra is 0, and that works only if the group is connected. So for a connected Lie group G, so the Carton model is the polynomial algebra on G tensor with the forms on N, and then you take the invariance. Okay? So that's the Carton model. And then it has a differential that we call the Carton differential. Now, I didn't work out the formula for the differential last time, but it is really the same as the one-dimensional circle case. Okay, so we let, say, x1 to xn be a basis for the Lie algebra G, okay, which is the Lie algebra of G, and U1 to UN be the dual basis for G dual, okay, then S of G dual, it consists of the polynomials U1 to UN, and D, the Carton differential, D is given by, okay, D alpha is D alpha minus, now for the circle bundle, it's just U I X alpha. But in general, what you have is the sum of UI IXI alpha. Okay, so that's the formula for the Carton differential. But where this D, in the Weyl model, when you apply it to theta and U, you have a formula that's given by the structure equation in differential geometry. But here, in the Carton model, you define V to be 0. You define DUI to be 0. Okay? So D is 0 on the symmetric algebra. Okay? And it's the usual derivative on the differential forms. Okay? All right, so that's the Carton model. Mm-hmm. And the Equivariant Theorem theorem says that the Carton model computes equivariant cohomology. Right? Equivariant theorem. Okay? And here we do need the hypothesis that G is a compact Lie group. Let me see, where do we use the compactness? Okay, I think when we go through the proof, we'll see where we need the compact. Oh, yeah. So, we constructed the universal bundle only for a compact Lie group, right? We said that the universal bundle is an infinite Stiefel variety. And that's because the orthogonal group acts on the infinite Stiefel variety. And so the universal bundle for the orthogonal group was the infinite Stiefel variety. And any compact Lie group can be embedded inside an orthogonal group. And therefore, any compact Lie group is a closed subgroup of an orthogonal group, and therefore its universal bundle is also the Stiefel variety. And this, we will meet in the proof of the Equivariant Theorem theorem. So let G be a compact connected Lie group. Okay, so acting smoothly on a manifold N. Okay, then there exists an algebra isomorphism between equivariant cohomology with real coefficients and the cohomology of the Carton model. Okay? Yeah. Okay. Now, Carton actually proved this theorem only in a special case for free action. Okay. So in a paper in 1950, it's a very famous paper which is published in the Proceedings of a Conference on Topology, on algebraic topology. And but Carton has a very special style. That is, he doesn't write down any details. He doesn't write down any computation or proofs. He basically just write down the theorem, and then a few lemmas, and then he just says, then you get this, you get that. But there are no details. Okay. So it's very hard to figure out, his proof. Yeah. Some of you write like Carton, in your homework. So, I took off points if you write like Carton, because I want to see the details. Yeah. A lot of people cannot understand Carton. So after he published his paper, there was a French mathematician. His name is André. And so he wrote a paper, that's like 100 pages, trying to explain what Carton did in, 5 pages. Yeah. But when it's 100 pages, it's very hard to read through. It's too much. Yeah. So, like 20 years ago, I tried to understand the proof of the theorem, and I just couldn't find anywhere, a satisfactory proof. So Gilliman and Sternberg, they have a book on equivariant drum theory, and they have a proof in it, but I think there's some place where there's a mistake in the proof, So I wrote to Gilliman and Sternberg to ask them about this particular point in their proof. And Sternberg said that they wrote that book in 3 months, and now he doesn't remember it. And Gilliman said, I'll respond at the end of the semester, but he never did, yeah. So, like sometimes you work on something and then you stop, you turn your attention to some other projects, and then you don't remember, what you did earlier. I think that's natural. It happens. I think it happens to them too. So I never got an answer from them, but I think their proof was not correct in the book called Supersymmetry and Equivariant drum theory. So then there are some other. Gilliman has a book with some co-authors, and in an appendix, he said you can prove this using the Mayer-Vittora sequence. So I had a student, who wrote, and again, Gilliman's book, that's just an appendix, and he didn't really have the details. He just said you can do this. So I had a student who wrote a master's thesis on the proof of the equivariant drum theorem, following the outline in Gilliman's book. And I think it is correct, but it's very long and it's different from Carton's proof. Okay? So it's only this year that I think I understood what Carton did. And, and then I could he did it only for a free action, and, I could extend it to an arbitrary action. So, and I think this is now an understandable proof. Okay? So, so I will just tell you, like the outline of how it works. Okay? But let's first look at the consequences of this theorem. So let's apply it to the simplest case when M is a point. Okay? Yeah. So call the equivariant Dirac theorem. So let's take M to be a point. Okay? Yeah. Then the equivariant cohomology of M it's the cohomology of the classifying space, BG. and we are looking at it with real coefficients. Okay? And then the theorem says that it's the cohomology of the Carton model with respect to the Carton differential. Okay? Equivariant theorem. And now the round complex on a point, it's just R, right? It's just the constants. There are no differential forms there. So you tensor R over R, so it's just the symmetric polynomials, okay? But the invariant ones, and then you have the. Okay. Now, what is this cohomology? Let's see. Yeah. Okay. Now.
But then you have to know what are the invariant elements.
Well, okay. The invariant polynomials, they are polynomials in U, right?
All
Huh? Well, no, it's certain polynomials in U that's invariant under the action of the group. Oh, I should have said that G acts on the Lie algebra by the adjoint representation. So it acts on the dual by the co-adjoint representation. So it acts on this by the co-adjoint representation. Okay. And G acts on the differential forms by pulling back. Okay, now this is the formula for the Carton differential. You first take d of alpha, okay, and this d is 0 on u's, so it's 0 on the polynomials. Okay, d is 0 on the polynomials, and then you have ui ixi alpha. Now alpha. Right now, here, it's just the polynomials in U. What is Ix on U?
0.
Yeah, it's 0 also. So D is 0 on the polynomials. Okay? If it's 0 on the polynomials, then it's 0 on the invariant polynomials, because the invariant polynomials are polynomials. Okay? And so the cohomology is just the complex itself. So it's just the invariant polynomials. Yeah. Okay? Yeah. So, so we have this result that the cohomology of the classifying space of a compact connected Lie group is just the invariant polynomials. Okay? And then it's actually not too difficult to show that invariant polynomials on the Lie algebra, that's isomorphic to polynomials on the Lie algebra of a maximal torus that's invariant under the Weil group. Okay? So this is an easy theorem. Because it's an easy theorem, there isn't a name attached to it. But Yeah, but I wrote out a proof in one of my papers on computing characteristic numbers using fixed points. So you can find that in the in this CRN, proceeding to CRN. That's the Center for Research in Mathematics in Montreal. And I think it was 2010. Okay, so let me just say where T is the Lie algebra of a maximal torus T in the Lie group G, and W is the Weil group, so it's the normalizer of T over T. It's the Weil group of T. Okay? Yeah. Yeah, so we have this theorem that the cohomology of the classifying space is the invariant polynomials on the Lie algebra, and it's also the polynomials on the Lie algebra of the maximal torus invariant under the Weil group. Okay? So we have this. Yeah. Yeah. So we can work out a couple examples. So let's take G to be the unitary group. Then the cohomology of B, the classifying space of the unitary group, it's when G is a unitary group, a maximal torus, it's the product of U1s, and that's just the diagonal unitary matrices. And so where Ti are in U1, so U1, that's the complex numbers of length 1, so it's a circle. And so the Lie algebra would be, the Lie algebra of the circle, but n times. The Lie algebra of the circle is, it's one-dimensional, so it's just a pure imaginary number. And so the Lie algebra of the maximal torus is the diagonal matrices, okay? Where each star is in IR. And then the Weil group okay, it's a normalizer over the maximal torus, and the normalizer it consists of the elementary permutation matrices. So it has a basis that's Eij. Okay? So Eij is a permutation matrix, so it's the matrix that's 1 in the Ij entry and 0 elsewhere. n by n matrix with 1 in the ij entry and 0 elsewhere. Okay? And then you divide by the maximal torus. Okay, when you do that, then what you get is just this symmetric group on n vectors. Uh-huh. Uh-huh. Yeah, so the bar group just permutes, okay, these entries, and therefore the polynomials on the Lie algebra T, the polynomials on the Lie algebra T, that would be just a polynomial with n variables. So it's R u1 to un. Okay?
Excuse me, what is the NCT, the basic EIJ? That is not a group.
So what do you mean by
Or this is a group. It's these are the generators. Yeah.
Subgroup generated by.
Yeah. So maybe I should say, yeah, groups. Yeah. So with generators. Uh-huh. EIJ. Oh, right. So I think, sorry, it should be 1. Yeah. Okay. Yeah. It should be like this, right? Yeah. It should be like this. So.
0 in II and JJ.
Right. Yeah. Yeah, it should be this. IJ. Yeah. Okay, yeah, so it's not, that's right, it's not this. It's, yeah, it's this n by n matrix.
So it's NGT, the group of permutation matrices. Correct.
with T? All with T.
Yeah, this would be the,
So it should be the group
yeah,
generated by T and these.
yeah, it's, okay, these are the permutation matrices, but you can, but T is in this, right? So, yeah, so it should be the group generated, yeah, that's right. So the group generated by T and the permutation matrices. And then you mod out by T. Okay? Yeah. So EIJ, I think I can write it like this. So it's E1, and then in the ith place you put EJ. So, okay. So it's E1 to EI minus 1, and then EJ, EI plus 1, and then EJ minus 1, EI, EJ plus 1. Okay, is this matrix? Yeah. It's the identity matrix, but you permute EI and EJ. Okay? Yeah. So that's the permutation matrix. Yeah. And so the polynomials on the Lie algebra T that's invariant under W are the symmetric polynomials in U1 to UN. Okay? Yeah. And so this is the cohomology of the classifying space of UN. Yeah. Okay. Yeah. So you see the equivariant Carton theorem, it cannot be too easy because in the simplest case, when M is a point, it already gives you this theorem. It tells you what the cohomology of the classifying spaces are for any compact connected Lie group. Yeah. Okay, so now, let's look at Carton's proof. Okay, so Carton's theorem is a very simple statement. It actually computes the cohomology of the base of a principal bundle. This is Carton theorem on the cohomology of the base of a principal bundle. Okay. So it says that if P to N is a principal G bundle, then the cohomology of the base can be computed from something like a Weil model. It's the cohomology of the Weil algebra of G, tensor with the forms on P, and then you take the basic elements in it. Okay? So let's see how this implies the equivariant Carton theorem for a free action. Okay. Now, so you need to know that if G is a compact Lie group acting freely on the right on M, then when you take the quotient and you look at the projection map, it's a principal G bundle. Okay. Now, this is not true if it's not a compact Lie group. So, for example, when you have the the torus, and you have the irrational line. You can think of that as the action of the real line on the torus by sending it, to other points on the irrational line. And the quotient, is not a manifold, and the projection map is not locally trivial. Okay, but here, if G is a compact Lie group acting freely, then maybe first we should say the quotient is a manifold, and this map is locally trivial, so it's a principal G bundle. Okay, so here M is a manifold. Okay, now this is a kind of like a standard theorem on group actions, and you can find the proof in Lie's book on manifolds. Okay, so if you have a free action, then you have a principal bundle, and then you can apply Carton's theorem. So by Carton's theorem, the cohomology of M mod G is the cohomology of this Lie model. Okay, now the total space is M. But the cohomology of the Lie model, and then if two spaces are weakly homotopy equivalent, then they have the same cohomology. So the equivariant cohomology is the cohomology of the homotopy quotient, and that is going to be the cohomology of M mod G. Okay? So this is a theorem in algebraic topology. If the homotopy groups are isomorphic, then the cohomology groups are isomorphic. Okay, and then we say that this can be computed from the Carton model. Okay. So that gives you the equivariant Theron theorem for a free action. Okay, so now let's look at an arbitrary action. So this proves the equivariant Theron theorem for a free action. Now, again, we want to compute the cohomology of the homotopy quotient, but when you have an arbitrary action, so the homotopy quotient it's e.g. cross M divided by the diagonal action. So you have the group G acting on EG cross M. And that action is free, right? Where G acts freely on EG cross M. Now, you already know how to compute the cohomology of the base when you have a free action. So you apply Carton, and you conclude that the cohomology of the base is the cohomology of the Weil model, right? So this tensor with EG cross M. Take the basic elements, right? Now, what's wrong with this? Yeah. The problem here is that EG is not a manifold. So you can't really take the Ram complex of EG. Okay? So this doesn't quite work. Because EG is not a manifold. It's infinite dimensional. However, for a compact V group, we know that EG is the infinite steeple variety. Okay, of K frames in an infinite vector space. So a compact V group G, you can put it inside some orthogonal group OK. So EG is the infinite steeple variety VK infinity. And this can be approximated by a finite dimensional manifold, by VKN for n large. Okay. Now, by approximation, what we mean is that they have the same cohomology, okay, such that for any k, the case cohomology of VKN Oh, that's bad. Let's just say I. For any I, the ith cohomology of VKN and VK infinity are the same, okay, if n is large. And, well, you know that VK infinity is contractible, so it's got the cohomology is 0 for n large. Okay? That's what it means to be an approximation. And, pardon?
Is this, did you fix I and
Yeah. I fix I,
N depends on I?
and then n depends on I, yeah. But the thing is, I have only finitely many i's, right? Because, wait a minute. No, this I could increase, yeah. Okay, I have to fix an I, yeah. And then NG is EG cross N over G. So this can be approximated by EGN cross N over G, okay? And because G is a compact Lie group which acts freely on this manifold, the quotient is a manifold. So this is NGN. That's the definition of NGN, okay? Yeah. And, yeah. So if you are computing a particular cohomology, then you can assume that your space is the quotient of a finite dimensional manifold. And then you can apply Carton theorem, okay? And so, so Carton theorem applies, and so you have a Weil model, and then you show that it's isomorphic to the Carton model, yeah. And so this will give you the equivariant, the Carton theorem in general. Okay. And and so what's left is that then we have to prove Carton theorem, and Carton theorem. Yeah, there, here. Yeah. So to prove Carton theorem, so what he does is this, like he puts omega p inside the Weil model, right? And this inclusion, commutes with contraction and the Lie derivative. So it takes basic forms to basic forms. So you have this inclusion. And then he calls this B and this B bar. Okay? And because you have an inclusion, then you can take the quotient and get an exact sequence. So you have a short exact sequence. And a short exact sequence gives rise to a long exact sequence. You get a long exact sequence in cohomology. Okay? And this is the cohomology of the basic forms upstairs. So this is just the cohomology of the forms on the base. The base is actually called N. Okay? So that's the cohomology of N. And this is the cohomology of the Weil model. You want to show that this is an isomorphism, so it's enough to show that this is 0. If you can show that that's 0, then you have an isomorphism here, and that's Carton theorem. And to show that any cohomology is 0, all you need to do is to be able to write down a cochain homotopy between the identity map and 0, right? And so Carton writes down a cochain homotopy for this. And it's a very clever formula, but if you have that formula, you verify that it's a cochain homotopy, then you know that the cohomology is 0, and so that proves the theorem. Okay? Yeah. So I'm going to stop here because my time is up, and then you can read the details in the appendix that I had already sent you. Okay? So so today we're going to have a party at 6:30. All right. So you have the address, 林森北路67巷57号. So 林森北路 is like this. Now 67巷 is here, but it's actually it might be easier if you go on 长安东路. And then like somewhere here, there's an alley. And there's a bank here. Yeah. 富邦银行. 富邦.哎，邦要怎么写？这样？不是。哦，这样，耳朵旁。Yeah. So it's right here. Okay. Yeah. So if you go on 长安东路, you turn at 富邦银行, then it's right there. Yeah. If you go from 林森北路, it's actually quite far from here to here. All right, so I will see you at 6:30. Yeah. All right, good. So thank you very much. Now, I have given you a grade, so that is the grade that I will report to the university.